Hi, welcome to the Arcade School. I'm Randy Fromm. During this lesson we're going to be taking a look at the oscilloscope, and I'm going to show you how to use it, but before we get into that, I just want to take a couple of minutes to try to convince you not to buy an oscilloscope. You heard me right, don't buy an oscilloscope. Now hang on a sec, if you already own a scope, that's great. I'm going to show you how it works. I'm going to show you what all the knobs do. We'll look at the oscilloscope in great detail, but if you don't already own an oscilloscope, I want you to think twice before you go out and spend a couple of grand on an oscilloscope. First of all, don't buy an oscilloscope if you expect simply owning an oscilloscope to make it easier for you to fix things. It really won't. Often operators can't obtain schematic diagrams for the games. Plus, sometimes there are custom integrated circuits that make it very difficult to repair some video games. Also, don't go out and buy an oscilloscope if you've just hired a hotshot technician and he says that he absolutely has to have an oscilloscope or he can't fix anything. I know lots of operators that have oscilloscopes just sitting on the shelf collecting dust because they've lost the guy that knew how to use the scope and no one else in the shop knows how to use it. In fact, that may be why you're watching this program right now. Don't buy an oscilloscope if you're just repairing a few logic boards. If you have a reasonably priced, reasonably fast, reasonably competent logic board repair facility near you, and you're just repairing a few boards, it's really much more practical to send bad boards off for repair than to try to learn dozens, actually hundreds of different microprocessor and computer systems. And finally, don't buy an oscilloscope unless you're planning on becoming very serious about electronics. Very serious. I'm not kidding here. Just owning the oscilloscope and knowing how to use it actually doesn't help you fix anything at all unless you know how to interpret the display that you get here on the screen. You have to know how the electronic circuits work, how the components work, and if the waveform that you're looking at is different than what it's supposed to be, what could possibly fail to cause that waveform to look different. So just owning an oscilloscope doesn't help you fix things. And unless you're planning on becoming very serious about electronics, I do not recommend that you get an oscilloscope. So when do you need an oscilloscope? Well, there are times when you must have an oscilloscope. If you're going to be working on digital and microprocessor systems, you're really going to need an oscilloscope. And this includes video games, pinball machines, vending games are now digital, redemption pieces are digital, bill changers, bill acceptors have little digital boards in them. And so there's all kinds of equipment now that uses digital, what we call digital logic, and you really will need to use an oscilloscope to troubleshoot a lot of those kind of problems. If you're working on jukebox amplifiers, you'll probably need an oscilloscope. When jukebox amplifiers develop funny little distortion problems, very often the only way to track it down is with an oscilloscope. Very minor problems like distortion in an amplifier are often pretty difficult to find using just a digital multimeter. If you're the monitor specialist at a distributorship and you're working on lots of monitors, maybe dog monitors that other people have tried to work on and haven't been able to fix, you'll probably need an oscilloscope. In cases like this, you may find that the wrong parts have been installed or the part has been installed backwards. I've seen that more than once. In cases like this, just troubleshooting with a digital multimeter testing components may not lead you to the problem. And active, dynamic troubleshooting using the oscilloscope with the power on and the circuits up and working may be the only way to locate the problem. So what the heck is an oscilloscope? Well, basically an oscilloscope is just a graph drawing machine. It draws a simple graph that shows voltage in the vertical direction and time in the horizontal direction. Now, on the front of the oscilloscope, there's this grid here, and it's called the graticule. And the graticule helps you measure the voltage. The graticule is divided into divisions, and here you can see 8 vertical divisions. 1, 2, 3, 4, 5, 6, 7, 8 vertical divisions. And if you look real carefully, each division is also divided into 5 subdivisions for more precise measurement. The scope has a vertical position control that allows you to move the baseline up or down on the face of the graticule. To set the baseline, start with the input selector on ground. This disconnects the probe and grounds the vertical input of the scope, making it 0 volts. Then use the vertical position control to pick a convenient horizontal line on the graticule. For the sake of discussion, we'll put it right on the center. Right here we have a control called volts per division. It's also sometimes known as the vertical amplifier. The volts per division sets the sensitivity of the input. For example, if I set this on 1 volt per division, that means that for every volt that appears here at the end of the probe, the trace will move up 1 division. If I set it on 2 volts per division, it will take 2 volts here to move it up just 1 division. The next setting is 5 volts per division. For every 5 volts here at the tip of the probe, the trace moves up 1 division. The next setting is 10 volts per division. After that, 20 volts per division. And then finally, 50 volts per division. You can use the scope to read low voltages too. For example, at its most sensitive point, it's 20 millivolts. That's 20 thousandths of a volt per division. 50 millivolts per division, 1/10 of a volt, 2/10 of a volt per division, 1/2 volt per division. Let's scope the output of a typical video game power supply and take a look at it. And in fact, there are really 3 outputs, aren't there? There's the +5, the -5, and the +12. Let's take a look at the +5 volt output first, since that's the main power supply. And when we scope the +5 output, we see that the trace has moved up approximately 2.5 divisions. Again, here's the baseline set right in the center of the graticule. And we see that it's moved up 1, 2, about 2.5 divisions. I have the volts per division control set on 2 volts per division. If it's set on 2 volts per division and the trace has moved up 1, 2.5 divisions, we must be looking at 5 volts, right? Let's take a look at the -5 volt now. And when I move the scope probe to read the -5 volt, we see that the trace moves down. So positive voltage will make the trace move up from the baseline, where negative voltage makes it move down. And when we look at this thing, we can also measure the voltage here. Remember, I'm still set on 2 volts per division here on the volts per division setting. And we see now that it's moved 2 divisions. It's moved 2 divisions down. But wait a minute, only 2. It's supposed to be -5. It appears to be only -4 volts. And that's not unusual. I've seen the -5 be anywhere from -4 to -6 and still work perfectly okay in a video game power supply. Now let's try scoping the +12 volt power supply. And when I move the oscilloscope probe to measure the +12, wow, where'd the trace go? Well, remember we had the baseline set in the middle, and we're still on 2 volts per division on the volts per division selector. If it's 2 volts per division and I'm scoping around 12 volts, I expect it to be about 6 divisions, huh? And starting from the center, there's 1, 2, 3, 4, 5, 6. The trace is actually 2 divisions here above the top of the screen, above the top of the graticule. Well, when you get in a situation like this, you may wonder, where the heck is my trace? What's going on? There's always the beam finder. Every oscilloscope has a button or control called the beam finder. And when you press the beam finder, it shows you where the beam is. In other words, it actually compresses what we call the vertical sweep, the vertical circuit, and the horizontal, and shows you, and even brightens it up, and shows you where the trace is on the oscilloscope. In this case, it shows me that the trace is way up off the screen, and if I were to move the vertical position control down, I could see it. Of course, now it's all out of calibration, and I have to recalibrate the baseline. And I do that by setting the input selector here to ground and selecting a new spot for my baseline. You don't actually have to remove the probe. I just did that so you can see the selector here. Now, we have a couple of choices. We can either move the baseline way down to the bottom and stay on 2 volts per division. Let's see how that works. And here we see, again, here's the baseline, the first line up from the bottom. Here we see 1, 2, 3, 4, 5, 5 3/4, almost 6 divisions, so it's just under 12 volts. Or the other alternative is we can leave the baseline right in the center if we wanted to, but this time set the scope on 5 volts per division. Here's the baseline, and we can see that it's moved up 1, 2, a little more than 2 divisions. We're on 5 volts per division. If we've moved up a little more than 2 divisions, then we're looking at, around 12 volts. And around 12 volts is what it is. Measurements on the oscilloscope are not terribly precise. That may surprise you, but when the trace falls in between a couple of subdivisions, you find yourself saying things like, well, it's around 12 volts or somewhere near 12 volts, where if you were using a digital multimeter, it might say something like 11.78 volts. So the oscilloscope is not particularly accurate when it comes to measuring voltage. Every time you reset your volts per division control, it's a good idea to double check your baseline. Set the input selector on ground and then set the baseline wherever you want it. Now, in this case, if we're measuring, for instance, plus 12 or any positive voltage, I never expect the voltage, the trace to go down below the center, right? Because we're not looking at anything that's negative. So you can set the baseline down at the bottom. Just another quick word about the probe itself. This is actually known as a times 10 probe. There's 2 different kinds of oscilloscope probes you can get, a direct probe and what we call a times 10 probe. Virtually all of your work will be done with a times 10 probe. In the times 10 probe, for every 10 volts here at the tip of the probe, only 1 volt is applied to the oscilloscope. Without the times 10 probe, the maximum voltage this oscilloscope would be able to handle would be 40 volts. That's 5 volts per division and 8 divisions. With the times 10 probe, the maximum is 50 volts per division, and the oscilloscope can display waveforms of up to 400 volts. So virtually all your work will be done with the times 10 probe. Let's look at some other things with the oscilloscope. There are some common signals that you'll see a lot, and this is certainly one of them. This is what your AC power looks like on the oscilloscope. It's called a sine wave. And this is, if I set the baseline here right at the center, that's 0 volts. The baseline is 0 volts or ground. And what you see here is the sine wave alternately positive and negative. This is the positive half cycle, and this is the negative half cycle down here. Here's another waveform. It's called a triangle wave, for obvious reasons. The triangle wave is very similar to another waveform called the sawtooth. And here's a typical sawtooth waveform. Again, for obvious reasons, it looks just like the teeth in a saw. You may also see a square wave like this. This signal is very common in digital circuits. It's called a square wave because it's approximately square. Another variation of the square wave looks like this. Here we still see that the waveform is basically square, but we see some very small, very narrow pulses that go in the down direction. You'll see plenty of other waveforms as well, of course. Most of your digital circuits look something like square waves. In something like a monitor, however, you'll be seeing all kinds of interesting waveforms, and we'll be taking a look at some monitor waveforms toward the end of this lesson. Well, let's take a look at a few more examples and see exactly how we measure voltage using the oscilloscope and using the graphicule on the front. For example, here's a triangle wave. And right now my volts per division knob is set on 0.5 or a half a volt per division. So I have a half a volt, 1 volt, and I see 2 subdivisions. Well, if it's a half a volt for each major division and there's 5 subdivisions, each one has to be worth 1/10 of a volt. So it's 1/2, 1 volt, 1.1, 1.2, 1.2 volts. Here's a square wave. It's exactly 1, 2, 3, 4 divisions. I have the volts per division set, again, on 1/2 a volt. So this must be 2 volts. Here's a sawtooth waveform. In this case, 1, 2, 3, 4, 5, 6 divisions. I'm set on 2/10 of a volt per division. 6 times 2/10 is 1.2 volts. And if it helps you, just count up. To be honest with you, I'm not very good at mathematics. In fact, I'm not very good at all at mathematics. So all I do is look at the volts per division knob and see, okay, it's set on 2/10 of a volt per division. And then I just start counting. There's 2/10, 4/10, 6/10, 8/10, 10/10, 1, of course, and another subdivision. So it's 1.2 volts. That's all you have to do. It's really pretty simple. Let's look at another one, and you'll see what I mean. Okay, here's a sine wave. Let's count the divisions. With the sine wave resting on the second from the bottom line, I have 1, 2, 3, 4, 5 major divisions and 1.5 subdivisions. So 5 major subdivisions and 1.5 times 5 volts gives me somewhere around 26 volts, but it's a lot easier if you just count up. Look, it's 5 volts per division. So you just go, okay, 5, 10, 15, 20, 25. It's a little less than half. It's about 27 volts, something like that. I mean, yes, you can count up. Each subdivision is 1 volt, and it is 26 and almost up another subdivision. It's almost 27 volts. In oscilloscope work, to be honest with you, that's close enough. Here's another sine wave. In this case, I'm on 2 volts per division, and again, counting up, I see 2, 4, 6, 8, 10, not quite 12, 11.5 volts or so AC. Here's those pulses we saw earlier, and if we take a quick look at the baseline, we can see it's right there, and count up, I'm on 1 volt per division, 1, 2, 3, 4, about 4.5 volts, which is a really good, solid, what we call a TTL level. Now, you may have noticed that most of the waveforms we've been looking at have been in this range. They've been in this kind of 3 or 4 division range, and that's really where you want to keep it. You don't want to have your volts per division set too small, because you will not be nearly as accurate when it comes to counting subdivisions. The larger you can make your waveform, the more accurate your counting will be, obviously. In addition, there's another circuit we'll look at later on called the trigger circuit. And the trigger circuit depends on a waveform of a certain size, a certain amplitude, as we call it, in which to trigger. And if the waveform is not large enough, you can see that it doesn't trigger properly without messing around with something. It's called the trigger circuit. We'll take a look at that later on in this lesson. Here's something else you may encounter. An AC signal that is riding on top of a DC signal. For example, in this case, you see that the waveform is partially off the screen. If I set the input select to ground, you can take a look. Here's my baseline down here. So what we're seeing here, whatever this is way above the screen. Beam finder, of course, brings it down in, and you can kind of see that it's partially up there. But this is not at all uncommon to have some type of a signal riding on top of what we call a DC bias. To eliminate that DC bias so that we can see the signal, you can flip the input select knob or the input select control to AC. And what that will do is, if there's any DC on the signal, it completely removes that. It completely ignores that, so that you can set the input to ground, set your baseline in the center, then flip the input select, and let me remove the probe just so you can see what it looks like. Input select to ground. This side is DC, where we've had it so far to measure those DC voltages. There's ground, and on the other side, this is AC. Let me put the probe back in here. When I flip the input select to AC, we can see the actual waveform. We can see the whole picture. Where before, remember when I had it on DC, because of that DC bias, where is that thing? Well, it's way the heck up here. It's way off the screen, way up there. When I flip the oscilloscope to AC, what that does really is it puts a capacitor in series with the input of the oscilloscope, and one of the properties of a capacitor is that it will pass AC through but block DC, and that's exactly what's happening here. That DC bias is being blocked, and what we're seeing is just the waveform. So use AC anytime you want to see a little bit of the waveform riding on top of a DC bias. When you have the input select to AC, you will most likely have the baseline set in the center, since that will be 0 volts, and it will automatically center itself on the baseline anyway, and then look at whatever the signal is. Again, that's setting the input coupling to AC. Oh, by the way, when you have the input coupling device set to ground here, you are not actually grounding the tip of the probe. In fact, you are disconnecting the tip of the probe completely from the circuit and grounding the input of the oscilloscope. This oscilloscope is what's known as a dual channel oscilloscope. There are actually 2 separate vertical inputs. They're called channel 1 and channel 2 in this oscilloscope. They may be called channel A and B in other oscilloscopes. And that enables us to look at 2 different waveforms at the same time. Now, in actual fact, the oscilloscope can't really draw both channels at the same time. There is only one beam back here, one electron beam, which is, of course, what's really drawing the picture on the front of the screen. So it has to time share the beam. And it does this in one of a couple of different ways. One is called alternating. And when it's set to alternate, here's what the beam really does. Let me just put these on ground here so you get a better idea. First, the oscilloscope draws channel 1 completely from start to finish. Then it draws channel 2 completely. Channel 1, channel 2, channel 1, channel 2, over and over and over again. And if it's sped up, and I'll show you later on how we speed things up, they seem to move so fast that all we see are 2 continuous lines. When I show you the waveform by flipping the input coupling to in this case, AC, just to make it convenient, you see the 2 waveforms. If it's slowed down, you can see that what's really happening is first one channel is being drawn and then the other. This is called alternating. And alternating is best when you're viewing fast-changing waveforms. The other method of displaying 2 waveforms simultaneously is called chopped. And the same control can set it to be alternate or chopped. What the oscilloscope is doing is displaying first a tiny section of one waveform and then a tiny section of the other waveform. A tiny section of this one, a tiny section of that one. They're so tiny that you really can't see that it's chopped up. And this is best for displaying slow-moving waveforms. If you use the chop setting on something that's moving too fast, it will appear to be segmented. That is, instead of being made of a continuous trace, it will appear to be made out of dashed lines. There's another vertical mode setting on this oscilloscope. It's called add. This setting takes the input at channel 1 and adds it to the input at channel 2. The result is shown on the display. At first glance, the 2 vertical channels look identical, but channel 2 has one extra button. It's called the invert function. When the invert button is pressed, the channel 2 input is flipped upside down. Why the heck would we ever want to do that? Well, if you use the invert function and the add function we just looked at, the oscilloscope performs what's known as an algebraic subtraction. Now, just bear with me here. It's not anything that you will really ever have to do as a technician. But if you have a small undesirable signal that you want to look at, and it's mixed in with some other signal, that's your source signal, you can put that source signal in channel number 2 and invert it, and then add the two together. And what that will do is subtract your main signal from the signal that has the undesirable signal in it. It'll subtract those two, and what's left is only the undesirable thing, the thing that you want to really take a look at. To be honest with you, it's just not something you're ever going to have to do in your normal everyday use. And to be further honest with you, I have never, ever, ever had to do it as a video game technician. Another control in the vertical section is the variable volts per division. This is adjustable. If I turn the variable volts per division knob, I can adjust the size of the picture. It is no longer in cal, or in calibration, and you can hear it click and feel it click into a detent. Listen. And that's the locked calibrated position. You can observe larger waveforms by bringing it down. Let's say the waveform is this big, and you want to take a look at it, and you're already on 50 volts per division. I suppose you can use this variable control to bring it down into where you could see it. I wouldn't recommend it. So why the heck would they have a variable control? Well, say, for example, you're a manufacturer working on the same piece of equipment all the time, and there's something that you have to set to be exactly, let's say, 1, 2, 3 main divisions and 3 subdivisions. You have to make something that tall. Let's say I'm on half a volt here. Let's say that's half a volt, 1 volt, 1.5, like 1 3/4 volts or so. That's kind of difficult. Like I said, with the oscilloscope, voltage measurements aren't all that accurate. So you go, well, it's about 1 3/4 volts. But suppose you do it this way. You get one good calibrated unit. You adjust your volts per division control so that you have instead exactly 3 divisions, let's say. You really want to make it as large as possible. So you have exactly 3 divisions. With that calibration knob set there, whatever it is, whatever piece of equipment is that you're working on, you adjust the pot on it, whatever it is, so that that waveform is exactly 3 divisions now, which is much easier to visualize than what it really is, which is, 3 main divisions and 3 subdivisions. But as a matter of fact, it's very easy to make mistakes if you start messing around with the variable control. If you do not leave the variable control calibrated and you're making all kinds of other measurements, they're going to be way off. You're going to think that you're reading a much lower voltage than you actually are. So I highly recommend that you don't mess around with the calibration knobs in the center. In fact, there is a probe calibrator that comes with almost every oscilloscope. In fact, it probably does come with every oscilloscope, but I kind of hate to say that since I'm not familiar with every oscilloscope. Most oscilloscopes have a probe adjustment. In this case, it's a little hole right there. And you put the probe in that hole, and it generates a square wave on the screen. In this case, it's about 1/2 volt. Let's see. Let's put it on 1/10 of a volt per division. Here's our baseline right here, and we can see, well, let's set it right in the center here. You can easily see we have 1, 2, 3, 4, 5 divisions, 1/2 volt. So that's what the probe calibrator output is telling you. It's going to give you exactly 1/2 volt out of that little hole, and in this case, you see that the scope is calibrated properly. Most good oscilloscopes have another control. It's known as the bandwidth limit control. This one has one, of course, and it's right here. It's called bandwidth limit, BW limit. The purpose of the bandwidth limit is this. Very often when you're trying to look at a signal, it might have some other weird high-frequency noise mixed in with it. That can make it difficult to obtain a stable picture. The bandwidth limit limits the bandwidth or the frequency range from 100, the normal upper bandwidth of this oscilloscope, to just 20. And watch what happens when I press this in. You see how the display settles down? Because it's not falsely triggering on a bunch of garbage. So unless you are looking at very high frequency pulses, you can leave the bandwidth limit, in my case it's just a push button, you can leave the bandwidth limit switch pushed in, and that will enable you to trigger much easier. However, if you are looking for very fast pulses, you have to make sure that you leave the bandwidth limit switch out. If you leave it in, you're not going to be able to see those very fast pulses that you're looking for. The horizontal section of the oscilloscope is also known as the horizontal sweep or the horizontal time base. Remember how the graticule was divided into vertical divisions? Well, it's also divided into horizontal divisions as well. There are 10 major horizontal divisions and the usual subdivisions within each major division. And if you recall the volts per division control that we used before to set the number of volts per division, well, there's also a seconds per division control right here, and that sets the speed of the horizontal sweep. Right now the horizontal sweep is set on 1/2 second per division. That means it takes 1/2 second for the beam to move each division as it sweeps from left to right across the face of the graticule. The next step up is 2/10 of a second per division. That means that it takes just 2/10 of a second for the beam to move across each division, each horizontal division. The next setting is 1/10 of a second per division. Now remember, there are 10 horizontal divisions, and as you can clearly see, it takes 1 second for the beam to move from left to right across the full width of the graticule. The next step faster is in milliseconds. That's thousandths of a second. And it's 50 milliseconds per division. That's 50 thousandths of a volt for the beam to move one horizontal division. I'm sorry, 50 thousandths of a second for the beam to move one horizontal division across the face of the graticule. The next step is 20 milliseconds per division. And after that, 10 milliseconds per division. And as you can see now, the beam is flying so fast across the screen from left to right that it's starting to look just like a solid line. Remember that 5-2-1 sequence that we saw previously? Well, here's the same thing in the horizontal time base or the horizontal sweep. Right now we're on 10 milliseconds per division. The next step, 5 milliseconds per division. Lost my probe here. Well, it's starting to move so fast now that we can speed it up more, and it's not going to look like much. So let's take a look at a signal now, and this is the signal coming out of my little test box that I have down here. Let's speed up the horizontal sweep and see if we can make some sense of what we have on the screen. There's 2 milliseconds per division. 1 millisecond per division, that's 1/1000th of a second for the beam to move across each horizontal division across the face of the graticule. There's a 1/2 millisecond per division, 0.5 milliseconds per division, and I'm starting to see the individual peaks that make up the waveform. Next step, 0.2 milliseconds per division. Again, the sequence is 5-2-1. Here we're on 0.2 or 2/10 of a millisecond for each division. there's 1/10 of a millisecond per each division. And we can clearly see the waveform that's being generated by the pattern generator. Now we move up into the microsecond range, millionths of a second, microseconds. The next step up is 50 microseconds per division. Now remember, it's really just a beam moving from left to right. And as the beam moves from left to right, the vertical amplifier that has the signal coupled to it is making it move up and down. And what we see is the triangle wave that we looked at earlier. Now we're on 20 microseconds per division, 20 millionths of a second per each division. At this point, we're moving so fast, that is to say the beam is moving so fast, that we're going to stretch this waveform out to the point that we won't even be able to recognize it. This pattern generator is generating a fairly slow signal compared to what this oscilloscope is capable of reproducing. This is a 100 megahertz oscilloscope. That means that this oscilloscope is capable of displaying usable waveforms up to 100 million cycles per second. Right now we're on 20 microseconds per division, then 10 microseconds, 5 microseconds, 2 microseconds, 1 microsecond per division. You can't really tell what you're looking at here even. That's 1/millionth of a second for each horizontal division. Then half a microsecond, 0.2, 0.1, and finally the fastest speed is 0.05 microseconds per division. In fact, the beam is falling by so fast I actually have to turn up the intensity to even see what we're looking at. And what I see is a tiny little bit of what's known as ringing over here. It's really barely discernible, and nothing unexpected, certainly. But right now, this beam is moving really quickly from left to right. 0.05 microseconds per division. That's 50 billionths of a second for the beam to move each horizontal division on the graticule. Quite often the waveforms that you're looking at are what's known as periodic waveforms. That is to say, the waveform will repeat itself after a certain period of time. Let's take a look at a typical periodic waveform. This is that sine wave that we looked at earlier. Remember, that's what your household AC power looks like, a sine wave. And we can see that it's the same pattern over and over and over again. We can measure the period of the waveform and tell exactly how long it takes for that waveform to happen. And it's real simple. First of all, you want to line up the waveform so that it's along some easily recognizable point along the graticule. There's a horizontal position control that enables you to move the beam left and right on the face of the graticule. And just pick a convenient point. For example, it's pretty obvious that this point and this point and this point are all exactly the same. Here's where the waveform repeats. Or you can look at it down here, where the waveform repeats down here. Just find some convenient place on the waveform that is obviously the same point over and over again. And use the horizontal position control to line it up. For example, if we line this peak up, this positive peak up on this line right here, let's count the divisions. 1, 2, 3, a little more than 3. It looks like about 3 1/3 or so. Let's see if we can get a little more accurate. Remember, there are subdivisions here, and if we use the vertical position control to drop the peak down where we intersect the subdivisions, we can take a better look at it. And here again I see 1, 2, 3 major divisions, and it looks like about two subdivisions. So it looks like it's somewhere around 3.2 divisions. 3.2 divisions. What does that tell us? Well, we need to go over here and look at the seconds per division control and see where that's set. And at the moment, it's set on 5 milliseconds per division. That's 5 thousandths of a second per division. We have about 3.4, actually 3.4, 3.2, 3.4 divisions there times 5 milliseconds per division. And again, instead of doing the math, the easiest thing is to simply calculate it out. It's on count it out. It's on 5 milliseconds per division. So you say, well, look, here's 5, 10, 15, maybe 16 and a half or so, 16 and 3/4 milliseconds, something like that. Well, I happen to know that it is, in fact, 16.66 milliseconds. And I know that because that's the period of our standard 60 cycle or 60 hertz AC power. 16.66 milliseconds is the period of our 60 hertz power, and it's a number that you're going to come up against again and again when you're troubleshooting. So it's a number you'll learn to recognize. And here we have just over 3 divisions, and it looks like about 16 and a half. And remember that oscilloscopes are not particularly accurate when it comes to measuring not only voltage, as I mentioned earlier, but also the period as well. And you end up saying, like I just did, well, it's about 3 divisions, a little bit more, and it's like 16 and a half, 16 and 3/4, somewhere in that range. And that's really as close as you ever have to get for our applications. One thing that can help you measure period properly is to use a waveform that's reasonably spread out. You need to be able to see at least 2 peaks, and for instance in this case I really can't tell where it repeats because I don't see 2 peaks. And so I set it up right here. If you have the seconds per division set too slow, and you'll see quite a few peaks, you may think that that makes it easier for you, and you might be able to line up a peak on one of these major divisions that way, but the closer they are together, the less accurate you will be. So you really just want to see, you really just need to see one complete cycle in order to tell the period. But here I can't really tell what one complete cycle is. Apparently, well, I could kind of tell actually, because certainly from here to here is one complete cycle. For example, we're on 2 milliseconds per division right now, and if I set this up, here's 2, 4, 6, 8, 10, 12, 14, 16, but I can't really tell where the waveform ends at that point, and so I wouldn't really trust it. I like to see at least a couple of good complete cycles so I can tell for sure what the period is. Well, I'm sure it comes as no surprise to you that 60 hertz or 60 cycles per second is the frequency of our AC power, a 120 volt AC power line. But how are frequency and period related to each other? Okay, you math majors, this one's for you. Frequency and period are inverse reciprocal functions. Now, hang on, don't freak out. It's not really all that complicated. In fact, it's pretty darn simple. 1 divided by the period will give us the frequency. And 1 divided by the frequency will give us the period. For example, our period is 16.66 milliseconds. It's actually 16.66666 milliseconds. 1 divided by 16.66 milliseconds, which converted into seconds, don't forget, is 0.016666 seconds. Remember, it's 16 milliseconds, 16 thousandths of a second. So it's 0.01666. 1 divided by 0.01666 equals 60. 60 hertz, 60 cycles per second. That's our frequency. On the other hand, 1 divided by 60 equals 0.01666. 16.66 milliseconds, our period. So it's really simple. 1 divided by the period equals the frequency, and 1 divided by the frequency equals the period. Let's take a look at a couple of other examples. Let's take another look at the sawtooth. We saw this guy previously. And here you can see that it repeats from here to here. Again, you know, I could have it smaller like this, but it'll be more accurate and easier to count the divisions this way. And if I move the waveform using the horizontal position control and line it up, I see that I have 1, 2, 3, 4 divisions before it repeats. The seconds per division, or horizontal sweep control, is set on 50 microseconds per division. So it's 50, 100, 150, 200 microseconds is the period of this waveform. 200 microseconds. 1 divided by 200 microseconds, and that is 0.0002. 1 divided by 0.0002 comes out to be 5,000. That's 5,000 hertz, or 5 kilohertz. That's the frequency. On the other hand, if I take 1 and divide it by 5,000, I end up with 0.0002, or 200 microseconds, which is the period. Now, in the real world of technicianing, you very rarely have to actually make those calculations. And when you're dealing with game repair, jukebox amplifier repair, you will never have to make those kind of calculations. Essentially, you're just looking to see if the waveform is there and what it looks like and what the voltage is, and you really don't have to worry about calculating frequency or period. It is helpful to be familiar with certain periods and certain frequencies because you come up against them again and again. For example, 16.66 milliseconds, the period of our AC power, happens to be the same period as the 60 hertz vertical deflection circuit in a monitor. And speaking of monitors, there's the horizontal section. That's 15,750 hertz, and you'll find that a horizontal period of approximately 63 microseconds, a periodic waveform that lasts about 63 microseconds, is very common because that's the period of the horizontal deflection circuit in the monitor. Here's another periodic waveform, and again, you know, we could look at it like this, but and in this case we can clearly see, you know, where the period, where the waveform repeats itself. But if we stretch it out, we can count these guys a little better, and what we see here is, here's obviously where it repeats, or repeats as the case may be. 1, 2, 3, 4 divisions. Well, I'm on 0.1 millisecond per division. So it takes 0.1, 0.2, 0.3, 0.4 milliseconds. That's the period of the waveform. 0.4 milliseconds is 0.0004, and 1 divided by 0.0004 is 2,500. And again, that's 2,500 hertz, or 2.5 kilohertz. In the case of a square wave like this one, you can pretty much line it up anywhere, and each one of these is obviously where the waveform repeats. Let's spread it out a little bit, and here we see 1 division, 2, 3, 4, and again I have a little bit more than that. If I use the vertical position control to move it down to where the subdivision is, I can count 1, 2, 3, 4 major divisions, 4.2, 0.4, 0.6, 4.6 divisions. And the horizontal time base is set on 20 microseconds. So we have 81.2, whatever it is, microseconds is the period. And again, instead of multiplying it out, just count it out. It's 20 microseconds per division. So 20, 40, 60, 80. Well, halfway through would be another 10. It would be 90, actually. I was wrong when I calculated it in my head, wasn't I? Halfway would be 90, and it's a little bit more than that, 92 or whatever it is. And that's really as close as you have to get. To be honest with you, I'm a really great technician, but I'm just lousy at math, and so I don't even try. And I'm not trying here for the sake of this program either. It's much easier to just count it out and say, look, I've got 20 microseconds per division. How many divisions? 20, 40, 60, 80. Use your brain. Half of that would be 10. That would be 90, and a little tiny bit more, maybe 92 microseconds. And that translates to a frequency of around 11,000 cycles per second. Sometimes we need to take a really close look at a very tiny portion of the waveform. And of course, we can expand this out quite a bit using the volts per division control. But say, for example, we wanted to look at a very tiny piece, something known as a spike or ringing. Right here on the top of the waveform, there is a very, very tiny spike. You can barely see it. It's sticking up right here on the top of the square wave. Let's say, for example, I want to take a close look at that. If I use the seconds per division control and try to expand that out, at one point I'm going to make it so big that it's completely off the screen. Even if I use the horizontal position, it's gone. Actually, we can see a little bit of it over here. We can't expand the time base out anymore to take just a look at that spike without expanding it out so far that we don't see anything at all. There's a way that we can look at just a tiny portion of that waveform. Just in this case, let's say we're just interested in the spike. If you use the horizontal position control and line up the waveform so that what you want to look at in great detail is right on the center, then in this oscilloscope, it's located right here in the center of the seconds per division control, a control known as times 10. This may be a button that's located elsewhere in the oscilloscope. It may be some other kind of a control in your oscilloscope. Watch what happens when I pull out the times 10 knob. The sweep has expanded to 10 times its original size. For example, right now the sweep is set on 5 microseconds per division. When I pull out the times 10, we're now at 0.5 microseconds per division, and we can get a better look at this little glitch here. Now, it's somewhat unstable, and that's perfectly normal. When you start getting into very, very fast time settings, you can expect some instability in the waveform. And don't forget, when you're done using the times 10 magnifier, remember, reset it back to its normal position. This same control acts like a variable knob, kind of in the same manner as we saw when we were looking at the vertical volts per division. Remember how it also had a calibration knob right in the center. The horizontal sweep also has a calibration control in the center and a detented, locked-in, calibrated position. Again, there's almost no reason for you to take this out of its calibration position, and in fact you can get in a lot of trouble again if you're trying to make periodic waveforms, periodic waveform measurements, and you don't have the horizontal sweep control in its calibrated position. So make sure that that's in its calibrated detent before you start making any periodic waveform measurements. Another really neat thing that the oscilloscope can do. Remember the times 10 magnifier that we looked at before? We can pull this out and expand the sweep times 10. There's another really excellent way that you can do this, and it's called delayed sweep. B, delayed sweep. Remember how the vertical circuits we had two, channel 1 and channel 2. Well, there are also two sweeps, or two horizontal time bases as well. One is called A, and the other one's called B. This selector, called horizontal mode, selects whether you're using the A sweep or the B sweep. In fact, there's even a way that you can use both. When I flip this to the A alternate B position, I end up with the two sweeps. And this particular oscilloscope does have another control called A and B sweep separation that I can use to separate the two. The position control moves them both up and down. The separation control moves the two. The sweep on the top is my normal A sweep. This is your normal sweep, and it's a sweep that you use for 99.9% of all the work that you do on the oscilloscope. When I flip it to A alternate B, it kicks in the B sweep, and here's what we can do. The seconds per division control is for A and B. If I pull this knob out and turn it, I'm speeding up the B sweep. And you can see the B sweep here on the bottom is moving faster than the A sweep. Not only can I select a faster sweep speed, but on the top I can see what part of the waveform I'm illuminating. Look, the B sweep is a little bit brighter. Watch as I increase the B sweep speed. I'm selecting a smaller piece of this waveform to look at. If I turn down the intensity, you can really see that what's illuminated here is what's down here on the B sweep. Not only that, I can select where on the A sweep I'm going to expand it. This control is known as the vernier. It's called a vernier. And what it really is a multi-turn potentiometer. Watch what happens as I adjust the vernier control for the B delayed sweep. I can adjust where on the A waveform the B sweep picks up and ends. Let me turn up the brightness a little bit more. Remember, that's what the waveform looks like. In fact, I can select a very small portion for the B sweep and display that. Again, if I turn down the brightness, and I can adjust the intensity of the A sweep and the B sweep here with separate intensity controls. If I turn down the intensity of the A sweep, you can see what we're selecting with the vernier control is just this small part. And I can select a very, very small part of the waveform and examine it on the B sweep. As we get faster and faster, brightness becomes a problem. And so sometimes you'll have to darken the room. In this case, for the sake of this video production, I have a lot of studio lights up here, and so that's kind of washing out the image, but if I shade it, you can clearly see what we're looking at here. So again, you can select just the A sweep. You can select just the B sweep, or you can select A, alternate B, and what that allows you to do is select which portion of the A sweep you're going to stretch out with the B sweep. The B delayed sweep allows you to look at a very, very tiny portion of a waveform and expand it out as large as you'd like to see it in greater detail. This is very handy when you're working with video because it enables you to pull out one individual line of video or even a single blanking or sync pulse and look at it separately from the rest of the signal. Well, now we come to what is probably the least understood or perhaps the most misunderstood section of the oscilloscope. It's called the trigger section. Think about a video game for a second. You know how in a video game we have a sync signal, a synchronization signal. It's a separate wire that comes from the computer board and goes into the monitor and keeps the monitor synchronized with the computer. Without the sync signal, the display would be completely useless. It would be completely scrambled and you wouldn't be able to tell what's on the screen. Well, in order for an oscilloscope to show a stable waveform like this, it also has to be synchronized. Somehow the sweeping beam has to be synchronized with the signal that's coming into the probe. Unlike a video game, there is no separate sync wire coming from the signal you're looking at to the oscilloscope. You only have the one probe and it carries the signal from the circuit you're working on to the scope. What the scope triggers on is changes in voltage. What the oscilloscope is looking for is some change in voltage, either a rising voltage or a falling voltage, like the rising voltage here on what is known as the leading edge, or the positive slope of the waveform, or a falling voltage, as it is here on the trailing edge, or negative slope of the waveform. On the oscilloscope right here, there's a slope select button, and when the button is out, it triggers on the positive slopes, and when the button is in, it triggers on the falling or the negative slopes. There's a level control over here, and this is an extremely important knob. The level control sets the level at which the oscilloscope will trigger. That is to say, it sets the voltage level at which the oscilloscope is looking for a change in voltage. If the level control is not set properly, the trace will run. Usually, it's just a matter of slowly rotating the level control back and forth until the oscilloscope triggers properly and the display is stabilized on the front of the screen. In this oscilloscope, when the display is triggered properly, the triggered LED lights up. There are 3 push-button switches that set the trigger mode for the A sweep. In the normal setting, the oscilloscope will not show a baseline until it is triggered properly. You will not see anything at all. As I rotate the level control, watch what happens as the scope triggers. As soon as the oscilloscope triggers, the display comes up. The normal setting is your most accurate setting. That is to say, you won't see anything unless it is properly triggered as it is here. There's also an auto trigger. In the auto trigger mode, if the display is not stabilized, that is to say, if the display is running like this, you will still see the baseline. You'll see this. You'll see something on the screen. It won't be stabilized until you trigger it with the level control. And again, you'll notice that the trigger LED lights up when it's triggered. Plus, of course, the display stabilizes on the front of the screen. To be honest with you, this is the setting you'll use most of the time. If you leave the scope in the normal mode, it can be very confusing because you don't see anything at all unless it's triggered properly. You don't know where the beam is unless you hit the beam finder and see what's going on. It can be really confusing. So you leave it in the auto mode unless you have trouble triggering it. If you have trouble triggering it where the display runs like this, you may want to put it in the normal mode, set the trigger properly until the display does come up, and then you can set it back in the auto mode and it'll be properly triggered. I really caution you against leaving it in the normal trigger mode because you're back to square one with oh my God, where's my trace, where's my baseline, where's my display, what the heck is this scope doing? I can't use a scope. This is a very common mistake. Just leave it on auto trigger and you'll be in much better shape. Stay away from the normal trigger setting. There's another button called the single sweep reset. When I press the single sweep reset button in, the ready light comes on. Then when the oscilloscope receives a pulse, and I'll just trigger it by touching the end of my finger to this probe, it triggers the oscilloscope and it makes one pass from left to right. Then you need to reset the oscilloscope again and the ready light comes on, and again on the next pulse it makes one pass from left to right. That ready light's very important because without the ready light you wouldn't know if you were still waiting for a pulse or if you had just missed it. So as soon as you press the reset button, the ready light comes on, and then on the very next pulse, it makes one sweep from left to right. This is also used quite often in more sophisticated lab situations where you want to take a photograph of the screen. To be honest with you, in the coin-op business, you will rarely use this function. By pressing in both the auto and the normal trigger button, this oscilloscope triggers on what's known as TV fields, that 16.6 millisecond period that it takes the monitor to scan one complete pass of the screen from the top to the bottom. That's really important since we use the oscilloscope to do lots of monitor work. The ability to trigger on fields is important. If your oscilloscope doesn't have the field setting, it's entirely possible to use the oscilloscope simply on a slow setting like 5 milliseconds per division and adjust the level control to trigger it properly. But it's real handy to have the field setting on your scope because that way when you want to work on a monitor and look at one entire field, you're telling the oscilloscope, hey, this is the kind of signal I'm giving to you and this is what I'd like you to trigger on. So the oscilloscope will ignore any higher frequency components in the video signal, such as horizontal components, and just look at the vertical components, the field signal. For triggering on television lines, this monitor uses the normal setting or the auto setting. Other oscilloscopes will have a separate setting for TV line, which is the horizontal frequency, 63 microseconds, or TV field, which is the vertical frequency, 60 hertz or 16.66 milliseconds. Remember the level control for the A sweep. And remember that we have two sweeps, an A sweep and a B sweep. Well, there's a similar level control here for the B sweep. And remember, the level controls the voltage level at which the triggering occurs. Again, like with the level control for the A sweep, the B trigger control is generally just rock back and forth until you obtain a stable display. This control tells the oscilloscope where to look for its trigger signal. The oscilloscope can trigger on the signal coming in channel 1, the vertical input channel 1, or it can look to channel 2 for its trigger source, or this oscilloscope has a setting known as the vertical mode. And in the vertical mode, it looks at both channels, channels 1 and 2. And finally, you can set the source for the trigger. That is to say, where the oscilloscope will be looking for its trigger signal. The source for the trigger can either be internal, line, or external. Let's take a look at the internal first. And the internal refers to the two vertical inputs, channels 1 and 2. When the selector is set for internal, we can tell the oscilloscope where to look for the trigger signal by selecting either channel 1 or channel 2. In this oscilloscope, there's also another setting called vertical mode. And in the vertical mode, the oscilloscope selects both channels 1 and channel 2 as its trigger source. Where would we want to use this? Well, this can be really handy when troubleshooting monitors. For example, in a monitor, everything is synchronized together. Everything is synchronized with the incoming sync signal. You can connect channel 2, the probe on channel 2, to the incoming sync signal, the signal coming from the logic board or the pattern generator, and select the source for the sync to be channel 2. It doesn't matter what we're looking at on channel 1 now. We can do whatever we want with channel 1, and sorry, here's channel 1 right here. And the oscilloscope will remain synchronized on whatever's coming in channel 2. So you set the sync using the level control. You set the sync on channel 2. The sync input is down here on channel 2. And you can do whatever you want, scoping various parts of the monitor, different circuits on channel 1, and you will not have to readjust the level control or adjust the triggering in any way. It doesn't matter what you're looking at. If the source is set on channel 2, that's what the scope is triggering on, no matter what we're showing here on the display for channel 1. The line setting for the A trigger source, the line setting, refers to the AC power line. The oscilloscope actually gets its trigger signal from the AC power plug, the same plug that powers the entire oscilloscope. For example, right now I'm looking at a sample of the sine wave. That's our AC power line, but you can see it's moving all around on the front of the screen. As soon as I flip the source to line, it's going to trigger on the AC line input. Since what I'm looking at is the AC power line, it has to trigger when I set the trigger source to the line input. You don't use the line input very often as a trigger source, primarily when you're working on power supplies. In linear power supplies, you may want to look at just the AC ripple, the AC hum or the AC ripple that's naturally occurs in linear power supplies. If you just want to look at the ripple and you want to trigger on that, all you have to do is set the trigger source to the line trigger input, and any ripple on the power supply line will stay absolutely synchronized or absolutely triggered and stable on the front of the oscilloscope. There's even a way that we can couple another external trigger source to the oscilloscope. There's another jack here. That's the external trigger source. And with the selector knob set on external, we can couple another signal, a signal that's completely separate from the two vertical inputs to the oscilloscope, and trigger on that. Now, the oscilloscope will not display that signal in the normal way that it displays channels 1 and 2. The trigger view button enables me to see what the oscilloscope is triggering on. For example, here I have it set on internal source. Right now I'm showing you channel 1. Let's display, with the trigger view button, let's display the trigger and see what the scope is triggering on. And when I press the button in, what you see is this. Well, this is what's on channel 2. Right now I have the trigger source set on channel 2. So naturally when I press trigger view, it shows me the trigger source, which is channel 2. If the source is set on channel 1, then the trigger view will show me channel 1, which is what we're looking at. Even if I'm looking at channel 2, this will show me channel 1. Remember what you're looking at with the vertical input selector, channel 1, channel 2, or both channels 1 and channel 2, has absolutely nothing to do with the source of your trigger. You can trigger on 2, but look at 1. See, I'm triggering on 2. This is what's coming in channel 2, but I'm only looking at channel 1. Of course, I can look at both of them and trigger on either channel 2 or channel 1. Or I can just be looking at channel 2 and trigger on channel 1 or channel 2. Remember that the trigger has nothing to do with what you're looking at. In the vertical mode, you set what you want to look at, channel 1 or channel 2 or both. And in the trigger setting, in the trigger mode, you select the source. This is very important because I see people making common mistakes where they have a problem like this, where the display is running and they try using the level control and they cannot get this waveform to synchronize or to trigger no matter what they're doing, and they go crazy when in fact they simply don't have the source set properly. When I set the source to the proper input, in this case channel 1, I can easily trigger the oscilloscope and lock the waveform in place. Once we've selected the external trigger input as our source for the trigger, there's several different ways that that external trigger source can be coupled into the oscilloscope. And that's what this control does right here. One setting is AC. In the AC mode, all of the signals are coupled to the oscilloscope through a capacitor. Any DC is blocked. Also, any signals below 60 Hertz are attenuated. That is, they'll be reduced in size or reduced in voltage, reduced in amplitude. The next setting is DC. In the DC setting, everything from the trigger circuit, everything that's coupled to the external trigger input is coupled to the oscilloscope. And you can actually see this using the trigger mode, using the trigger view button. You can see what's going on with the trigger. So we have AC, we have DC. The next one is DC divided by 10. And what that means is that for every 10 volts coming in here into the external trigger input, only 1 volt is coupled to the oscilloscope. It's real easy to see that. If I depress the trigger view, here's our trigger signal that's coming in, our external trigger signal. Watch what happens when I divide it by 10. Here's external trigger divided by 10. And you can see that the signal has dropped quite a bit, and it's a lot smaller. Again, here's the normal trigger signal. Here's trigger divided by 10. And you would use the divide by 10 input coupling if the signal you were triggering on was too high a voltage for the oscilloscope trigger input. It's a lot of fun to work on monitors with the oscilloscope, and monitor waveforms can be very interesting. And very often you'll find pictures of the monitor waveforms printed in the service manual or printed on the schematic diagram. Using these waveforms as a guide, you can scope various circuits in the monitor to determine if they're working properly or not. Let's take a look at a few of them, starting with the video circuit. The signal that you're looking at is taken off of the collector of one of the video output transistors on the neck board of the monitor. I'm using both channels here. The trace on the top is the collector signal. The trace on the bottom is the sync input that's coming from my pattern generator. Remember I mentioned this earlier. I have the sync connected to channel B or channel 2, and I have the trigger set to trigger on the sync signal. That way I can look at anything on channel 1 or channel A and the trace will remain synchronized or triggered on the screen. Now what I really want to show you is this. This oscilloscope is made by a company called Sencor. It's the model SC3100. Actually, they call it a waveform analyzer because it does some fantastic things that a normal oscilloscope won't. For example, if I press the delta time measurement, I can illuminate just a small portion of this waveform. If I illuminate one of the horizontal sync pulses and illuminate the waveform to the portion of the other horizontal sync pulse that's exactly the same point on the waveform, I can measure the time period right off of the liquid crystal display. And here you see it says 63 microseconds. To convert that period into frequency, all I have to do is press the button, and the liquid crystal display shows us our frequency. The SC3100 is also known as an auto tracker because it has some unbelievable automatic features. For example, there's an automatic setting for the volts per division control. When this control is set on automatic, I can move the probe from one point in the circuit to another without resetting it. The voltage will automatically appear here on the liquid crystal display. For example, here I'm looking at a video waveform that's 4 volts peak to peak. I can move the probe over and measure the signal at the horizontal deflection coil of the yoke, which is 133 volts, without having to touch a single control on the oscilloscope. There's also an auto setting for the times per division or seconds per division control as well, and it performs the same function, automatically selecting the correct time base to show you the waveform that you're looking for. For more information about this remarkable piece of equipment and to obtain your free videotape on using Sencor products, give them a call at 1-800-SENCOR and tell them Randy Fromm sent you. Well, that's all the time we have for now, so I'll see you next time at the Arcade School. Bye-bye. That's it.